What's going on, guys? We're back with chapter 10 questions this time. We're going to start out with 38 and just do all of them in order. So 38 says, during a 6-second time interval, a flywheel with a constant angular acceleration turns through 500 radians that require an angular velocity of 100 radian per second. What is the angular velocity at the beginning of the 6-second interval, and what is the angular acceleration of the flywheel? So as always, we want to write down our knowns and our unknowns. So we know the time, and ignoring the solution here, we can already tell we're only given variables that we saw in our translational kinematic equations, similar. So the angular replacements of these, that's all we're given. So we know that we're going to use something similar to the kinematic equations. So let's just write out down everything we know so far. We know the time, and we know the delta theta. The angular displacement is 500 radians. And that it acquires a velocity, so its final velocity is given. Its final angular velocity, I should say. I'm really bad at drawing omega, to be honest. It looks pretty bad. Okay, it's kind of just like a W though. So we know that its final angular velocity is 100 radians per second. Alright, so this is everything we know. We also know the acceleration is constant, which might be helpful. Alright, so the first question, part A, asks what is the angular velocity at the beginning of the 6-second interval? So in order to find, we're finding let's write what we want to know. So we want to find omega initial, or the initial angular velocity. And the way we can do that is by referring to our formula sheet. As I stated earlier, this looks familiar. This looks similar to a kinematic problem in translational kinematics. So let's go ahead and go to our formula sheet. So if we go here, we can see, where is it? Okay, right here. Here is all our angular kinematic equations, I guess. So we're finding omega final. So we're going to use this equation because it's the only one that has all the variables except the one that we're looking for, or the one we have all the variables for except the one we're looking for. So yeah, all the other ones have acceleration, which we don't know yet. So we're going to write that one down. So let's go back. So the formula was delta theta, angular displacement, so the equation is delta theta 1/2 omega initial plus omega final times time so let's go ahead and plug everything in. Just zoom out a bit. So delta theta is 500 radians. Our W initial is unknown. Sorry, I keep saying W, oh my gosh. Our omega initial is unknown, and our omega final, they said it acquired 100 radians per second, its velocity, angular velocity. So 100. And then our time interval is 6 seconds. Alright, whoops. So this is our equation. So we're just going to isolate omega initial. So we multiply 500 by 2, so 1000, and then we divide by 6 to cancel out the 6 on that side. And then we want to subtract that 100, and that is going to equal our omega initial. So just put this in your calculator. Minus 100, and you should get omega initial equals 6.67 times 10 to the 1 radians per second. So that's part A done. What is the angular velocity at the beginning of the interval? So yeah, let's make sure we write that down. And we can check that in our solution here. So we did use the correct equation, and then I guess they used something a little bit different. Oh no, they just divided. They like isolated before they plugged in, but doesn't make a difference. But they did get the correct answer, and they used the initial equation like we did. So we did the right process. So that's part A done. Let's start with part B. It says, what is the angular acceleration of the flywheel? So now we're finding alpha here. So we're going to refer back to our formula sheet. And we can really just use any of these, I think, since we have all the variables besides acceleration. So I'm going to use the simplest one, which is the first one here. To me it seems like it's the easiest, I don't know. But you can use whatever one you want, as long as it has acceleration in it. So yeah, let's do that one. Alright, so we have our equation now. Let's write it down, just so we don't forget. It was omega final equals omega initial plus angular acceleration times time. So let's go ahead and isolate A just for good practice. It's probably a good idea to isolate the variable you're looking for first before plugging in. So let's go ahead and subtract omega initial. On both sides, and then we're going to divide by time on both sides. So this is our angular acceleration equals our omega final minus omega initial divided by time, which makes sense. Alright, so now we can plug in. So our final omega was 100 radians. I'm not going to write the units. And then we just found our omega initial up here in part A. It was 66. It was repeating, so I'll add another decimal place just for accuracy's sake. Yep, and then we're going to divide by 6 seconds. And yeah, all we have to do is plug it in to our calculator and see if we get the right answer. Alright, so after calculating, we see that our angular acceleration does indeed equal 5.6 radians per second squared. So that is part B done, and we can verify that by looking at the solution. And yeah, we see 5.6 radians per second squared. Alright, that's everything. That's both part A and B done. So hopefully this makes sense. All I did was write down all my knowns, write down all my unknowns. I guess I kind of forgot the angular acceleration there, but just write down your knowns, your unknowns, and then just solve each part. This is pretty straightforward for angular kinematics, so hopefully it makes sense. If it doesn't, then make sure to leave a comment. Try to go through the rest of these and put them in the same playlist. So yeah, hopefully you enjoyed. Again, make sure to leave a comment and like if you enjoyed. And yeah, thanks for watching.